For Christmas, I built a 3-foot candy cane rocket. For the 4th of July, I made a hydrogen gas generator. I love a good holiday, but I focused my projects on deeper dives into more complex systems. My first tactically controlled rocket used laser cut and cardboard components, but it didn't fly straight. I pivoted to a modular 3D printed design and built a custom Rust app for hardware-in-the-loop simulation to verify the flight logic on my desk. This led to a successful design, which I ultimately flew with rockets to nationals. I applied this technology to a wildfire detection rocket, featuring a propulsive recovery system with motors in the nose cone. To test the ignition and payload deployment systems, I did a static fire. The retro propulsion system was also successful. However, I realized standard servos had too much backlash for reliable rocket control. So I went down a rabbit hole of field-oriented control. I designed this dual-axis driver from scratch, which required a lot of time on the oscilloscope, but eventually worked. I also assembled my own boards using stencils and a reflow hot plate, which allowed me to prototype my simpler boards at home. I'm now applying FFC to an air brake rocket design. I optimized the linkage geometry and motion gen to have the highest mechanical advantage at the point of most drag. I also love applying technology to robotics, where I've plasma cut metal frames for my Science Olympiad robot. And as lead programmer of FTC 21229, I've developed some of the top-ranked autonomous programs in the world. This year, I'm doing FRC, using Advantage Kit to simulate the electrical and physical subsystems. I've also started work on a Rubik's Cube solver. And I started work on a 1-pound beater dog combat robot. Whether for a rocket launch or custom motor driver, I love to build hardware that combines complex theory with practical challenges.